Hey guys, welcome back. Day 27, second part. We're talking about orbitals and molecules right now. So how the actual orbitals and molecules exist, all right? And so we know when two atoms form a bond, because we talked about hybridization last time, and bond is a shared electron pair. When these atoms form a bond, the electrons in the bond are under the influence of two nuclei, and they are lower in energy than they were individual, right? They bond because it's favorable. They don't bond because it's unfavorable. Now, of course, humans, we try to design things, and like what you're watching this on is not a favorable bond, right? We had to make it, right? But they still, bonding is almost always energy released. Now the electrons now occupy out an orbital that belongs to the molecule, right? So we're getting towards this new theory called molecular orbital theory, right? And so when we talked about hybridization, right, we talked about that in Chem 1, only the central atoms hybridize. I don't know if I said that in the last video. Only the center atoms hybridize. The terminal atoms, we're not worried about them hybridizing yet. We take organic chemistry, they will, but right now they don't. We're not worried about that. Okay? Right now we're worried about which orbitals in space combine. So they have to have the same energies, right? They have to have the same space and the same symmetry, all right? What does all this mean? All right, well, let's just talk about the combinations. So one atoms and the quantum numbers versus two atoms and the quantum numbers. So we still have the principal quantum number and the principal quantum number, right? The secondary for one atom versus the secondary for two atoms. It's still an L, but it's just they use lambda, right? And so it goes from S, P, D to sigma, pi, delta, all right? And so what do we have here? The combinations. Sigma bond is a s orbital plus an s orbital, all right? I don't like how this is, yeah. All right, so hold on. The combinations of sigma bond, these are bonds. Let's talk about the combinations here. I want it more clear. And so you can have an s orbital plus an s orbital gives a sigma bond. An s orbital plus a p orbital can give a sigma bond. And a p orbital plus a p orbital can give a sigma bond. Now, I'm going to come down to this grid. X, Y, Z. All right? And so if I have two atoms, all right, two atoms, the axis going through the two atoms is the internuclear axis. So it doesn't have to be X, it is in this case, but this would be the internuclear axis. All right? And so that would have to be the internuclear axis. Right? That would have to be on the same, right? Because a P on the axis, right? Well, what's that going to look like? I'll use a highlight. I'm going to erase this, but here I can do it this way. A P on the internuclear axis is going to look something like that, right? Where this P orbital looks something like that, right? And so they would have overlap right here. If I had a P on the internuclear axis and a PZ, let's say, there is no overlap anywhere. There's no overlap, so they can't bond. All right, so that's what I mean. They have to be, so what are the common, it's PX plus PX, PY and PY, PZ and PZ. However, the internuclear axis could be any of the axes. So we got that going for us. That's what we get this display. For a double bond, it would be the sigma and a pi. And so a pi bonds would be a P something plus P something. I'm going to fill these in so that you know they're not on the inner axis. That's a pi. And we're also going to have, that's a double on the third bond. And then for the, maybe we can have a P and a D. And then there is a delta bond, the quadruple bond, and that's going to be a D plus a D, and that would be a delta bond. So those are our options, okay? So now the first bond, if we're going to do this, the first bond is going to be on the internuclear axis. Right? That's where our sigma bond is going to be. And that's going to be between atom A and atom B, right? Just on the internuclear axis, right? And so that's there. The second bonds are going to be off the internuclear axis. So we could have a vertical p orbital and a vertical p orbital, right? And what happens is they kind of make a new arrangement around the sigma bond. And so this down here in the mirror image up top, this, where I come coloring in, is where the, I guess there's all of this too. That would be a pi bond. So that's where the pi bond would be. And it's both it's both above and below. It's the same pi bond. Now there could be another pi bond, which would be in and out of the screen. It's very hard to draw, but it'd be in and out of the screen. Like if I had the PY and the PY, and they go around the sigma bond in and out of the screen. All right, and so we're not going to worry about a delta bond because that's only in metals. So it just depends on what on what orbitals are on there. So for example, assume that the internuclear axis for nitrogen is the, let's call it X just for simple, the X-axis. What orbitals? One from each N contribute to a sigma bond and to the pi bonds. That's a good question. So if you look at nitrogen, nitrogen is 1s2, 2s2, 2p3, right? And so 1s is full, 2s is full, 2p, right? And we have up, down, up, down, up, up, up. So we have core, full, and then 1, 2, 3 bonding opportunities in the p orbitals. So it's the p orbitals that are going to overlap. So if this is my x-axis, I'm going to have what orbitals? Well, S is full, so S is not bonding. And right now we're going to say that we're not hybridizing because there's no central atom. So it's just what orbitals are on the x-axis? Px plus Px is the sigma. And then you have pi. Well, if vertical is going to be Y, no, vertical is going to be z. All right? So vertical z, pz plus pz can be a pi, just like in this picture above. And then we have y, so it means py plus py can be a pi. All right? And so we have the sigma on the axis, because you'd have two atoms of nitrogen. You have N1 and N2. The sigma would be right here. You'd have 1 pi above and below. And then you have the other one on the sides. So that's how it kind of would work. All right? If you put your eyeball right here and you look down the internuclear axis, right, you would see the internuclear axis being a dot. You would see you wouldn't even see the sigma bond. The sigma bond would be right barely there. But you would see a pi bond that's vertical, and you would see a pi bond that's horizontal, like that. So that is me putting your eyeball down the axis here, right? So if we're looking down the x, and that's x, right, we would see pi here and pi here, right? Those are pi bonds. We would not really see the sigma bond. I know it's very abstract. A lot of students struggle with this, and that's okay. It's not a major part of the course at this point, but I want to tell you it exists. All right, and that leads us to the next topic. Molecular orbital theory, MO theory. All right, again, this is not a huge part of the course, but it's very important. All right, and so when we talk about bonding theories, right, quantum mechanics is a mathematical model that we use to help us understand what's going on with the bonding, to help us predict what's going to happen. Valence bond theory, if you had to know one for Chem 1, Chem 2, and organic chemistry, it'd be valence bond theory. Because that does a very good job of predicting behavior for carbon and whatnot. Okay? Especially those small molecules, or non-metal molecules. A lot of metals, like what I used in grad school, we did a lot of MO theory to talk about electrons and where they're going, because we did a lot of electron transfer stuff. All right, and so MO theory treats the molecule of having new atomic orbitals. All right, and since we want new atomic orbitals for the molecule, right, we approximate a wave function for the molecule instead of the atom. And so both theories, valence bond theory and MO theory, have their applications, and they both have their weaknesses, and they both have their strengths. All right, and so MO theory, we talk about this as orbitals, waves, right? Because orbitals are basically wave functions or waves, and how they combine, right? And so when waves combine, right, waves can combine and add to each other and make themselves bigger, and waves can combine and cancel out, right? In fact, some luxury cars have sound waves that cancel out road noise, so it's quieter, right? Kind of, it's amazing, right? It's kind of neat, right? And so when these atoms interact, there are waves that are going to be in phase and waves that are going to be out of phase, all right? And so what do I mean by that? If I have a wave function and it goes up, down, up, and then down, right? Positive first, then negative, right? And if this one, right, goes positive first, then negative, they're in phase. However, if it goes there and then there, and that's a negative, they're out of phase, all right? So, right, it's a better thing would be sine x plus sine x, right, is 2 sine x, right? However, sine x minus sine x is 0, right? And so it just depends if we're in phase or not out of phase, right? And so we're going to get there. So let's look at this, all right? The MO diagram, you guys can probably already read all this stuff, right, on the screen. So all the number of orbitals is the same. And what happens is you get the number of orbitals, half of them are in phase, half of them are out of phase. And we call the in phase ones bonding and the out of phase ones non-bonding, all right? Again, I'm not going to hammer this home to you guys, but this is what it is. All right. And so we have, if we look at this, I already made them for you. You got a hydrogen, and I'm going to make the hydrogen highlight. You got the blue hydrogen, all right, and you got the purple hydrogen, all right. And so there's one S is all we have. So if you notice, this, that's for the purple hydrogen, and that's for the blue hydrogen. That's their individual orbitals. They each have a 1s, okay? What they do is they mix. You can see a solid line. Sometimes you see dotted lines. We always drew dotted lines. They mix for the molecule of H2. And so this is the bonding orbital, and this is the non-bonding. Sometimes it's called, with the star, anti-bonding, all right? Because it's out of phase. And just like other electron configurations, you put the however many electrons you have, you just fill in bottom up. So we'd start like one there, and then we'd keep going, all right? So for helium, you got 1, 2, 3, 4 electrons, right? So when we mix, HB mixes and HA mixes, HE, right? And so we mix, we get these orbitals again, right? Because you have same thing. Helium A, and this is helium A's orbital. You have helium B, and helium B's orbital. Then you have the bonded one, He2, and these are helium's He2's orbitals, all right? You got a bonding and anti-bonding, right? And up here it talks about the bond order, right? And so the bond order is the bond electrons in bonding molecular orbitals, which for helium, right there, 2, minus electrons in antibonding orbitals, there, 2. 2 minus 2 would be 0 divided by 2, which is 0. So helium-2 does not exist. Hydrogen, I have 2 bonds, all right, in bonding, so that's 2. Nothing there, so that's 0. So 2 minus 0 is 2, divided by 2, 1. It's a single bond. That's the bond order, all right? Okay, and again, this is about all I'm doing with it. I'm going to show you the next, how these go, because they do. But lithium, boron, carbon, nitrogen have these MOs, and oxygen, fluorine, and neon have these MOs. All right, so how does this kind of work? Right? If you notice, all right, these are the combinations, and they're in a different order. So sigma 2s is always the lowest energy, and then sigma, well, star, it should be, oh yeah, this is the P. So sigma 2s, sigma star 2s, those are the bottoms, all right? And then we have here, the pi bond is lower in energy than the sigma bond for these. That's something you'd have to memorize. Don't memorize it, you're not going to do it, all right? But these just fill in, just like this. Right? If you ever had to do it, they would fill in like this. All right? This explains some properties in oxygen. Right? So for oxygen, O2, how many electrons do we have? Right? Our valence would be 12. Right? 6 and 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's how oxygen actually works with its MO diagram. And so it's bond order. We did bond order, all the bonding ones. Bonding, 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 right? 2, 4, 6, 8. 8 minus antibonding, 2, 4. 8 minus 4 would be 4 divided by 2. 2, it's a double bond. That's great. Oxygen is got 2 unpaired electrons. You wouldn't know that looking at the Lewis dot structure, the valence bond theory. But one thing oxygen does, and your book actually shows this to you, almost every textbook in Chem 1 shows this to you, is oxygen is magnetic. It's what we call paramagnetic because it has unpaired electrons, these 2 unpaired electrons. That makes it paramagnetic. And what does that mean? It means liquid oxygen responds to a magnet, which is amazing, right? And this theory shows you how that works, which is cool. Now, again, I'm just showing you how that works. These are the MOs of all of them, right? From lithium to neon, okay? And it tells you diamagnetic means there's no magnetic properties. Paramagnetic means there is a magnetic property. So B2 does. Carbon's not. Nitrogen's not. Oxygen's magnetic. Fluorine's not. And of course, E2 doesn't exist. It wouldn't exist. All right? Those are the MO diagrams of lithium through neon in group 2. Or period 2, excuse me. But that's it. I am not big on this. I am much more in with the hybridization and whatnot, but I wanted to explain it to you just in case. Hopefully that helps. Hopefully that clarifies what's in the book. If you have any questions, don't hesitate to reach out. Otherwise, we'll see you next time, guys. Take care.